students, Ms. DeLeo here. Let's start on our section 4.2 notes. We're talking about describing the variability in a data set. So there are three measures of variation that we will discuss. So there aren't three ever, but there's three that we will really discuss. And they include the IQR, interquartile range, the range, and the most important, standard deviation. Both of these measures tell us about the spread of a particular data set. So let's talk about how we find the range, just in case you don't remember. The range is your maximum value minus your minimum value. And your characteristics of the range are that the larger the range, the more variability in the data set. So basically, the range tells us our possibilities. By giving us a look at the minimum and the maximum, we get the number of possibilities that we have within a data set. So we know that two values in a data set can be no more than however many values apart, which is very important for us to understand shape and spread as well. All right, so let's move on and talk about some deviations from the mean. We're getting closer to standard deviation here. So the most common measure of variability describes the extent to which the sample observations deviate from the sample mean. So if we were in a perfect world and we did a perfectly wonderful job, all of our sample means would be very close to the population mean. However, we know that some observations are full of variety and they may fall away from the sample mean. So we'd like to see where they fall away, how they fall away in maybe a systematic way, and we want to put measurement to that. So to deviate means to stray or be away from. A deviation is positive if the x value corresponding is greater than the mean, and a deviation is negative if the corresponding x value is less than the mean. So the greater the amount of variability in the sample, the larger the magnitudes of variation. So the larger we expect the deviations to be. So by definition, a deviation is a data value minus the mean. Okay, which looks like this: data value 1 minus the mean. Then we've got data value 2 minus the mean, and so on and so forth. These are all different deviations. And it is always true that the sum of the deviations will be 0 for a symmetric distribution. That's because in a symmetric distribution, we are hoping that we have half of the data below the mean and half of the data above the mean. The mean is centered with the median and the mode. So therefore, if we look at values that are below the mean, they will be negative deviations, and above the mean will be positive deviations. And when we add them together, they will cancel each other out. Okay, so an average deviation is 0. So your average deviation would be also 0. And we cannot use this to measure variability. So we can't find out how far values stray from the mean. We can't find out if we have a symmetric distribution that's very flat and spread out, or if we have one that's very skinny and centered. We don't know, because looking at these deviations, they're summed together, and on their own, they don't really tell us anything. They just tell us how far a particular value is from the mean. So we had to come up with something different, which is why we use standard deviation and also variance. So variance is the sum of the squared deviations from the mean divided by n minus 1. Oops. Got excited. Divided by n minus 1. So here is your formula for variation. It's the sum of every deviation squared divided by n minus 1. Now, if we look at this, the sum of the squares, we will have only positive values now, so that this gives us kind of an idea of how spread out the data is. So, just so you know, your book notates the sum of the deviation squared as x sub double x. So that's just something to note. A smaller variance value, s squared is the notation for variance within a sample, indicates a smaller amount of variability in a sample, where a larger s squared value indicates a larger amount of variability in a sample. Okay, now we're getting to standard deviation. So the size, the definition of standard deviation is this is a size of a typical or representative deviation from the mean. So we don't have to look at individual values. We're looking at kind of the distribution all over and saying, okay, how do things typically fall away from the mean? Are they typically close, typically far? Is this a very spread out distribution? What is going on, okay? So this tells us how spread out data is about the mean. Okay, so at this point, we're going to be using S for sample distributions, and they're mostly for comparison purposes, okay? So S is the notation for the standard deviation of a sample. And S squared is the standard deviation, or my apologies, variance, the variance of the sample. So how we know up here we're talking about large and small values, this is also true, exactly true for standard deviation. The smaller a standard deviation value is, so the smaller an S value is, indicates a smaller amount of variety in the sample, where the larger an S value is indicates a larger amount of variety in the sample. What we mean by that is with respect to 0. So if there was no variety in the sample at all, we would have a standard deviation of 0. So this is with respect to 0, okay? So the closer we are to 0, the smaller your S and S squared values are. The larger they are to 0, larger or further away they are from 0, tells us that there's more variety. This is helpful when comparing distributions, not so much when we're just looking at one individually. At this moment in time, it will be important later, but for comparing and describing numeric displays, that's going to be very important as a measure of variation to understand. So how do you calculate the standard deviation from variance? This is a positive square root of the variance. S equals the square root of S squared, of course. And it's also important to note that you can use that calculator function, one variable stats, that we've been using to find the mean and the median for this too. And you can find the sample standard deviation under S sub x, underneath that one variable stats function. Okay, that is all dealing with the sample. If we get a standard deviation from a population, we use Greek notation of sigma squared for a population variance and sigma for a population standard deviation. And usually sigma is unknown, so we use sample data. However, sometimes sigma can be known. It's going to be something we have to look for. So this is very important to note. We must use values computed by the sample because sigma is usually unknown. When calculating the sample standard deviation, we divide by n minus 1. As you saw above, right here, we divide by n minus 1 when calculating the sample variance, and then therefore the square root of that is the sample standard deviation. Okay, so we divide by n minus 1 here for a sample. This will give us a closer value to what we believe the true population standard deviation is to be. Also, it will help account for the variety that we are aware different samples can produce. So if you are able to calculate the standard deviation of an entire population, you divide by n. So if we're talking about standard deviation for an entire population, sigma is the square root of the standard deviation squared, or the deviation squared divided by n, and then you take the square root. So when you use that one variable stats function, you're going to notice there's an S sub x function, also a sigma sub x function, and they're going to be kind of similar but a little off, okay? One represents the population and one represents the sample. Based off of the context of your problem, you have to decide which one to use. Last but not least, we're talking about the IQR, which is going to be very helpful for us when we start building box and whisker plots later this week, which should be a little bit of review. Your IQR is the interquartile range of your box and whisker plot, but also what it is it is Q3 minus Q1, which Q1 is your lower quartile and Q3 is your upper quartile. And your lower quartile is the upper boundary on the lower 25% of a data set. And your upper quartile is the upper boundary on the lower 75% of data. So the IQR basically tells us the range of the middle 50% of data. Which is really helpful because this can let us know the range of typical values, okay? So this gives us kind of a look at what typical values look like for our data set. Are they really close together? Are they really far apart? The interquartile range gives us kind of a look at our typical values centered around the mean. Really quick. We'll actually come back to what if n is odd later on when we are building box and whisker plots. So you can save this. And at this moment, you're actually probably not going to be calculating any interquartile ranges. Oops. You're not going to be calculating any interquartile ranges. You're just going to kind of be aware and know what the interquartile range is and what it means, so that when we build our box and whisker plots, next time we see each other, you are ready to go. Okay? That's it. I hope you guys have a wonderful Wednesday. Bye.